那近年来，无人机的发展是日渐普及，然后也越来越受到关注。那市面上也开始出现了很多跟无人机相关的模拟器或是游戏软体。那今天我们邀请拥有对马战鬼、中土世界摩多之影城市开发经验的Trevor Sundberg 张启武讲师为我们讲解他现在正在制作的写实无人机物理模拟模型的开发经验跟知识。
Thank you. Thank you. All right. Okay, so this is an idiot's guide to realistic FPV drone physics for games. If you're interested in just flying drones or learning about the physics of drones or flight physics, or even just learning to create a physics engine yourself for games, this would be a talk that's kind of interesting for you. So let's go ahead and get started. So my name is Trevor Sundberg. 你好，我叫张启武。我喜欢无人机。Thank you. I tried. All right. So a little bit about me. I worked at Monolith. I worked on Shadow of Mordor, if you guys know this game. It was a Game of the Year game. I also worked on Sucker Punch for Ghost of Tsushima, if you guys have played that one. I was a professor at DigiPen Institute of Technology, where I taught how to build game engines and how to build compilers, as well as like how to write programming languages. And so that was kind of my specialty. I'm also a licensed helicopter pilot. I just love flying. If any of you guys played Battlefield, that was my inspiration for actually learning to fly. So I've got a really good connection between games and like learning to fly because I think it's such a special thing to me. Also, I like jumping out of them. I'm also a skydiver, a licensed skydiver, because I really just love flight and physics and stuff like that. And more recently, I left games and went to the cloud. So I did a startup and sold the startup to Cloudflare. The startup was running the browser in the cloud so that you don't get viruses on your own computer. And then, I really just love to code. This is a picture of me when I was a kid. I built a computer out of cardboard, just kind of a fun little project I had. And then now I'm actually working on an indie game myself. And so I'm going to go ahead and show you guys the trailer for Kinmen Kill. Kinmen Sha. Thank you guys. Yeah. So if you're interested, I put a QR code up. Join the Kinmen Kill community and just learn to fly for Taiwan. This whole presentation is actually all live. So this was actually made in Unity. So I'm actually controlling it right now. This whole presentation, I'm going to release it so that you guys can go through the whole thing and test everything yourselves. There's also custom physics code that's written for this whole game. It's written in C. I'll be releasing this as an open source project, so you guys can get access to that too. Just get general news and updates about the game, and also just drone tips and tricks for building drones and really everything related to drones. I've actually brought a drone here, and you guys can feel free to come take a look at it after the fact, and I've got a lot of equipment down there too. Just join and have fun. All right, so let's get to it. So why care about drone physics? Well, one of the first big reasons is that drones cost money, lots and lots of money. So when you crash, it's really bad. It's devastating. You have to buy all new parts and everything. And the big part of it is you really can learn to fly in a simulator, in a game. And so one of my favorite games on Steam is called Liftoff. It's basically just like a racing game where you race FPV drones. Before I even learned to actually fly a real drone, I got 100 hours in that simulator, and I was surprised at how well I was actually able to fly a real drone when just coming out and trying it out and just like, able to fly around and not run into things and not cost money. I called this an idiot's guide because prior to any of this, I had no idea how any of the physics worked. I didn't know how to fly a drone. I didn't know how to put it into a game engine. And so it was kind of my learning experience and kind of just giving this experience to you guys. Also, another big one was I tried to look up, like, how do I put drones into games? How do I get drones working in games? I couldn't find very good resources online of how you would actually do that, how you actually get drones into games, realistic FPV drones. And then another big one you guys have probably seen, in Ukraine, they've demonstrated, that cheap FPV drones are extremely effective. And then last but not least, we're going to have to write a custom physics engine. So a lot of this talk is going to go into the physics, and the reason is because, as we'll see, we'll have to write this physics engine and then attach it to Unity. Okay. So let's focus on quadcopter drones, but what kind of drones am I talking about? So on the left there, we have what are like the do-it-yourself drones, the ones that you build yourselves. And then on the right here, we have our commercial drones. So those are the ones you can buy off the shelf. The left drones, they're cheap, but they're difficult. They're extremely hard to fly. That's actually why we want a simulator, so we can learn how to fly those things. Versus the commercial drones, they're expensive. They're usually 5 times more expensive than the actual build-yourself drones, but they're really, really easy to fly. They kind of just take off. It just does a lot for you. One of the other things is that the drones you build yourself, there's minimal safety features. It's very easy to cut your fingers on those drones. Whereas the commercial drones, they have a lot of safety features that try to make it so that, it's not gonna hurt you, it's not gonna crash into things, just so many things to prevent that from happening. The flight time on the build-yourself drones, they really just attach a battery to it. They drain the battery pretty fast, so it's usually about 7 minutes, whereas the commercial drones can get anywhere from 30 minutes plus. They're meant for photography, taking lots of wide-angle shots and everything, so they usually last a long time and have a lot of battery optimizations on them. The max speed is probably one of the biggest differences, where the do-it-yourself drones can go up to 160 kilometers an hour, or oftentimes faster. They're very, very fast, and they can do a lot of damage if you run into something. Whereas the commercial drones, they try to limit that. Again, it's part of the safety features. They're trying to prevent that from happening. Another difference is, if you see here, the tilt on a commercial drone, it's pretty limited. Like, they don't want you to go very fast with that commercial drone. Whereas the tilt on our build-it-yourself drone is really kind of anything you want. It's unrestricted. It's because we can do acrobatics with that drone. And then the kind of related to the tilt, the max angular velocity. So how fast the drone is able to turn. Again, the commercial drones, they limit that a lot. Whereas the build-it-yourself drones, they can go quite fast. They could spin super quick. And probably the biggest difference, and the reason we're focusing on that for this talk, is that for commercial drones, it's closed source. Meaning that unless you get in there and hack into the thing and pull it apart, you're not going to get access to the code or what's actually happening under the hood. Whereas the build-it-yourself drones, it's usually open source. You can download the firmware off of GitHub. There's several different ones for running the drones yourselves. So, okay. One of the big differences, because most of you guys are used to game controllers, and so I have something here that's kind of like a game controller. This is a transmitter. So this is what actually sends the signal to the drone, and it can go for many, many kilometers to actually reach the drone. It's more precise than a gamepad. It has Hall sensors in it that are very, very accurate, so that you can get very accurate flight. And then I think one of the biggest differences is in game controllers, they're usually a circle. So it's kind of like this, whereas this is a box. And why that's important is because that allows you to get the maximum on each axis for your flight. So you have the pitch and the roll here as I'm showing, and I can get all the way down or up on one of these. As you can see too, it acts as a USB joystick. That's so that they can be used in simulators so that you can really practice with the real thing. And then probably one of the biggest differences, I always love doing this, maybe I can get the sound here. It's always kind of fun. So one of the biggest differences is that even though they return on this axis, we're all used to a gamepad, kind of comes back to the center, The throttle does not. It holds at whatever I set it at. So if I set it down, it stays down. And another thing is, the throttle, this is the default position, is the throttle being down. And the reason is because when you start your drone, you don't want the drone to just go when takeoff. So the drone won't even let you start unless the throttle is down like this. Another big difference is the input on this comes into the computer or to the drone at 150 frames per second or faster. So again, that's so you can get that very twitchy, very fast response on the drone. And so that also means that if your game engine is running at 60 frames per second, you're missing input from your controller. You're missing that high fidelity, fast input rate coming from the controller. Okay, so I'm gonna give just a little tiny demonstration here. Hopefully I won't crash it too bad. So this is what a drone looks like from a first-person camera perspective. So I'm kind of flying around, and this is just a test level that I have. So I kind of go through some loops. But one of the things I want to point out is that the drone, it can be very rapid. You can have all sorts of acrobatics, and then it's meant to be very twitchy and very fast the response, so that you can do things like, you know, turning around really quick or going through some loops. Let's see if I can. I'm not the best pilot, but you know, I can try. Oof! I just cost money there. Yeah, and so if I take a look at what this looks like also from the outside, this is kind of what we're going to be building. So these are kind of the physics forces that you'll see on the drone when you're actually like, you know, kind of putting this together, the debug view and the development view of it. And so you can see that's kind of our drone. Okay. So that's what we're building. All right, so games run at 60 frames per second, right, typically. Obviously they can go up and down, but you know, that's the typical target goal is 60 frames per second. And then the interesting thing is that the actual hardware on the drone itself, the computer on the drone, actually runs at 20,000 frames per second. And sometimes up to 50,000 frames per second. Way faster than a game actually runs. That's something I just learned doing all this. I had no idea before I started any of this. So if we're trying to do Unity or say Unreal, we can increase the physics rate, but in my own experiments, when I tried to increase Unity to do 200 frames per second or faster for the physics, it starts to break down. It starts to get a little bit slower, mostly just due to the fact that it's checking collision constantly. So we're going to go with a hybrid approach. We definitely want to use the physics engine in Unity because it's great, but we're going to go with a hybrid approach here, which is basically to use Unity's physics while the drone is colliding. So if the drone is on the ground or if the drone hits something, then we're going to switch to Unity physics. But then otherwise, we're going to write our own custom physics engine that runs at 8,000 frames per second. And we'll see why that number is actually very important, the 8,000 frames per second, in just a little bit here. Okay. All right, so let's get a little primer of just a little bit of math and physics going on here. So a vector is a direction in 3D space. So x, y, and z has 3 numbers. In Unity, y is the up vector. So in this example, I can kind of raise this up. This is my y. You see the y increases, the number in the middle, that's my x, y, and z. And I could go on any axis here and change that value. So that's what a vector is. That arrow you see pointing, that's the vector we're talking about. I also just mentioned this because if you're using another game engine or writing your own, Unreal, the z is the up vector. So just something to keep in mind when you're doing all this. For this demo, because I've written this whole thing in Unity, it's y will be the up vector. Okay. All right, so a force in a physics engine pushes an object. So a force itself is a vector. It's a direction in 3D space. And the length of the vector is how strong it pushes. So you can see here when I have a really long vector, it pushes pretty hard, and he gets pretty scared there. And then if I have a very short vector, it kind of goes, ee. But it can be anything. I could even fly with it because it's a 3-dimensional vector. And then smaller objects have less mass to them. And then smaller masses move faster. And what's interesting is that it's the same vector. The same length moves the object much faster for the same amount of force. And then as we saw before, bigger masses move slower. We're kind of all used to that, a heavier object. And the reason this is physics-wise, acceleration is equal to force divided by mass. So what that really just means is when the mass gets bigger, you're dividing by a bigger value, so it gets slower. Okay, so an object in motion stays in motion unless acted upon by another force. So this is a physics principle. And what that really means is that when I move this object around, it's just going to keep moving. I'm not touching the controller. I just give it a little force, it keeps on moving. Now normally friction from the ground or drag in the air would slow an object down, but in space we have very little friction or drag, so it's just going to kind of keep moving. And I can do wah. Okay. Now, in a physics engine, all the forces add together. So in this particular example, we have gravity pulling this box downward. But then we have the ground, and the ground is actually pushing the box back, what's called a normal force. And so those two are equal and opposite to each other. And because you add two opposite vectors together, that gives you the zero vector. And that just means that the object is not moving. So this object stands perfectly still until we remove the ground, which removes the normal force. And then he falls down. So you can see there, I'll just demonstrate that again. If I remove the ground, the top force goes away and the object falls down. Okay. So in a drone, each motor spins a propeller. So we're talking specifically about quadcopters, forward propellers. And when the drone is idling, when you have it on and actually active, it's usually around 3,000 rotations per minute, so the actual propeller is spinning. And then when you go to max speed, that's usually around 10 to 15,000 rotations per minute, so very, very fast. And the amount of thrust is going to go up as we increase that force. Okay, so propellers exert a thrust force. And then if you add all those up, this is what you do in a physics engine, if you add all those thrust forces up, you get lift. So the 4 different yellow ones added together gives you that kind of greenish blue one going upward. And then when a drone is hovering, just standing still in midair, that's when the thrust is exactly equal to negative gravity. So when the two vectors are opposite of each other, the drone will stay still and hover in space. Okay. So a little terminology just to kind of, for anybody not familiar with flight, pitch is that way we move forward. So this is how we're kind of pitching forward, leaning forward. And then this is pitching back. And that's a rotation on the x-axis. And now, again, this is kind of dependent upon the game engine you're using because the x, y, and z can change depending on like left hand, right hand, whatever. But because we're using Unity, y is up. So yaw is going to be a rotation around the y-axis. It's kind of like our turn, like turning our head. And then this one, everybody should be very familiar with because you guys love scooters and motorcycles. This is how you turn. Like this is a banking turn, a roll around the Z. So that's yaw, pitch, and roll, pitch, yaw, and roll. And there we go. Okay. So forward and backward flight, the way that's going to work is we're going to increase the back two motors, and that's going to cause our drone to tilt forward. And then if we want to go backwards, we're going to increase the front two motors, and that's going to cause our drone to tilt backwards. And if we do all of them at the same time, that's how we get our lift. So that's when our drone lifts up. And if we want to go forward, we tilt forward, and then all the vectors are pointing forward. Yeah. And so if we go backwards, I'll do that again, all the vectors will be pointing backwards. So that's how we do backward flights, because they're all pointing backwards. And then similarly, for side-to-side flight, we just spin up the left two, and that kind of tilts us to the side. So this is our roll. So this is a right roll, and this is a left roll. And we just spin up the other two. And again, if I go up and then go to the left, go to the right, this is how drones actually fly around in space. And if we do something bad, we make our bear mad. Okay. So this is one of the first things that confused me, so I just kind of want to point this out. Let's take a closer look at yaw turns. So yaw turns are basically the rotation around the Z or the y-axis that we were talking about before. So this is our yaw. Okay, so when I got this all running, I ran into this thing. I was like, okay, now I can pitch forward, I can roll to the side, and now let me yaw. And now let me do yaw. And then, why are you laughing at us? What the heck is going on? And yeah, it was like a very confusing moment for me. What the heck is going on? How does a drone turn? How does it yaw with only an upward force? If all of them are just pointing upward, how does it turn? And so, okay, we're going to come back to this problem, but we need to dive a little bit deeper into rotational physics to answer that problem. Okay. So, the center of mass is the average position of an object. And so that's where all the mass is if you were to like, you guys all know you balance something on your finger, that's the center of mass. So it's like if you had a needle and you were to put it there, that's going to perfectly balance on that point. In Unity Unreal, they're going to compute the mass of the object and the center of mass for you automatically. But and it's something to mention too, for like a lot of artists, they're used to like pivot points and rotational points in the engine. But in a physics engine, the only point that matters is the center of mass, because that's the point that all rotation happens around. Okay. Okay, so torque is the rotational equivalent of force. Torque is also a 3D vector that defines an axis of rotation. So looking at this is our little example here. This is the torque. That straight line that you see, that's the torque. And I've added some visuals to kind of help show the direction of what the torque is facing, but when I go back this way, it rotates it the other way. And the length, just like the force, is exactly how strong we push. If we do a little tiny torque, it just moves a little bit. If we do a lot, that's a very strong torque, and the object will move very fast. And then he'll do that. And again, as we mentioned before, the rotation is around the center of mass. Okay, so just to demonstrate, because it was kind of confusing to me too, torque can really be any vector, right? It's a little weird, but it's something where you can just kind of keep changing torques to any kind of direction. So just something to think about with torque. It was a little bit of a visual for me to learn that. Okay. So mass distribution affects the rotational difficulty. So in this particular example, if I go like this and I give it a torque, these are the exact same object. They have the same mass, but somehow the first object rotates faster than the second object. And the reason that is because each axis, even if it's the same object with the same mass, each axis of the object has a different rotational resistance. And that resistance is called the moment of inertia. And so physics engines will represent this moment of inertia with a 3x3 matrix. And if you're not super familiar, that's okay. But it's just kind of think of it like mass is a single number, just how heavy it is. This is a matrix that describes how hard it is to rotate on each axis. Okay, so where are we going with this? So when we picture a motor and a prop, we usually think of it like this. We got the motor, it's kind of sitting there, and then we got a prop that's spinning around. And if we spin it faster and faster and faster, it kind of looks like that. That's what we like imagine, especially even like a helicopter or something like that, just kind of sitting on the ground and then the prop is going around. As if the motor is fixed to the ground, but as usual, we take this into space and we're going to see something slightly different. Okay, so another physics principle, for every action, there is an equal and opposite reaction. So what that means is when the motor spins the prop, it's actually also going to spin the motor in the opposite and equal and opposite direction. So I'm going to kind of go over that again. If I start with a little force here, oops, let me do that again. If I start with a little force here, there it goes, and it keeps moving, but notice the prop is spinning the opposite direction of the motor. It's affected by the mass, but more specifically, the moment of inertia. Again, this is why we think of it like it's fixed, but really it's just that the motor itself is heavy and that the prop is much lighter than the motor. Okay, so coming back to the problem of how we actually solve this, how do we get yaw turns with the motor and propeller? And the answer is that when we spin the propellers faster, we actually have an equal and opposite torque applied to the body. So that's actually how they turn. If you can see that, the propeller actually spins faster. And you notice it's the diagonals. That's actually an important aspect of drones. So when the diagonal spins faster, it turns. When we lift up off the ground, all of them are going to start spinning. But the reason it doesn't rotate any direction is because they're all canceling each other out. We have two spinning one way and two spinning the other. So this is actually what turns look like when you're doing it with torque. And we made our bear happy. Okay. So to balance those motors, we need two going one way and two going the other way. And so this, for anybody learning to fly drones, this is called the props in configuration. This is the standard configuration for drones. It's because the props in the top are spinning toward the camera. The camera is the one going upward. And then notice that the diagonals are moving the same direction. And the reason that's important is because when we do any one of our maneuvers with the drone, say we go forward, that's again doing the backside, we need those to spin opposite from each other because we need them to cancel out so we don't cause a turn. Same thing with going backwards, same thing with going to the side. Those are all opposites from each other. And that's kind of the beauty of the diagonal configuration of drones. Okay. So, this is kind of what it looks like again with our forces and being able to do all of this. I'm going to try this. I'm pretty bad at this. This is called 3D flying. It's like not looking through goggles. But this is kind of what your drone will actually look like when it's flying, with all the torques on it too. And we made our bear happy. Okay. So another thing we haven't talked about is how do we go from the sticks on the controller to the actual motors. So we have, this is again the props in configuration. And the way that you kind of just do this is just looking at the drone, kind of just like, kind of what we talked about before. Just look at each of the motors and go, okay, when I pitch forward, the back two need to go. When I pitch backward, the front two need to go. And you kind of just write this down and map it all out to the right, to the left. And so what we're going to end up with, this is kind of seeing the yaw in another way. Notice that the props are spinning one way, but the body goes the opposite way. That's the equal and opposite. And then finally, last, the throttle. When the throttle goes up, all the motors go. So this is just how do we figure out which motors need to go when we're moving the sticks. And what this actually looks like in practice, if you actually look on a flight controller, it's actually just a matrix. So it's basically, if you see the matrix, there's all the plus ones in the first column. That just means all of them are affected by the throttle. Whereas if you can have the pitch and the roll, depending on whether it's negative or positive, that's where it's -1 or not. The reason why this is important is if you have a different drone configuration, for example, like an octocopter with 8 propellers, this matrix will become a 4x8 matrix. And it changes for there's many, many different types of configurations for drones. But obviously this one we're just focusing on quadcopters. Okay, so using everything we've learned up to this point right now, this is what flight is going to look like. But there's still a problem here. And I promise I'm not just like joking with this. I'm really going to be bad at flying this. And the reason is because there's going to be like extra rotation that we need to get rid of. And so we're going to go ahead and look at like what this looks like. So if you were to program this right now, you would actually have a drone that kind of flies. And I got to this point and I was like, this does not feel right. What am I missing? And so I kind of feel like I'm drunk, like wobbling around all over the place. And if I start this over again, it's like I can show it a little more often or more easily. I'll just start a rotation, and an object in motion stays in motion, which applies to rotation. I want to point out, I'm not touching anything on the controller, it's just going, right? Nothing is stopping that rotation. And so that's what we're missing for the drones. So, air drag, in the air will slow down a drone, but it's not enough. There's something else that we're missing. A gyroscope, which is a little electronic piece, measures the rate of rotation, the angular velocity or the speed of rotation on each axis. So as a little example here, if I move this, you can kind of see the gyroscope outputs a value and tells us how much it's rotating on each axis. If I go back to 0, it's nearly stopped. If I rotate it on this way, it gets faster and faster. This device is what tells us how fast the drone is actually rotating in real life. So the flight controller, and by the way, this whole thing is the flight controller. The gyroscope is actually just one little piece of that drone. The flight controller is going to stop the unwanted rotation by using that gyroscope information. So we're going to see how that actually happens in a little bit here. Also, just to mention, the flight controller is also what performs the motor mixing that we saw before with that matrix. So that's on the board this device right here. Okay. All right, so I want to demonstrate also what flight should actually look like. So this is using an open source flight controller, and I'm going to go up and I just want to point out how kind of A, snappy this is, but B, what actually happens when I turn. So when I turn and then I release the stick back to the center, notice that all the rotation completely stops. If I go like this, it kind of got a little wobble there, but if I go like that, it just stops. So if I watch the stick, it stops, it stops, it stops. The flight controller is using the gyroscope to make those changes. It's actually making corrections to the motors for us. So that's what we ideally want to see with our flight controller. And so one of the ways that I decided to approach this problem and trying to learn how it actually worked was to actually use a real flight controller and integrate it with Unity. So Betaflight is an open source flight controller that you can get and you can download off of GitHub. It's all written in C. It's what's used by pretty much every FPV drone racer. So any race that you see going on, it's all used by there. It's also used in Ukraine. It's what they use for the kamikaze drones. It's what performs motor mixing, as we saw before. We'll also see this. It also does the controller and the rates and curves that we'll see later, as well as the gyroscope and motor corrections that we've just been talking about. The flight controllers do so much more than just that, though. They have, for example, the actual UI that you see in the game, the HUD, everything you put when you put goggles on, that's all rendered on the drone itself. So all the UI that you see is actually rendered. They've got a graphics chip on there rendering out UI for you and then putting it on the video. So that's the thing that runs at 20,000 frames per second, upward to 50,000 frames a second. And a point there, the reason for that 8,000 number that we were talking about before is that that's the rate that the gyroscope runs. So the gyroscope samples its velocity, its angular velocity at 8,000 frames per second. So we want the snappiest physics possible. That's why we have to write a custom physics engine for Unity. And so just to demonstrate too, this is the actual tool. So part of one of the cool things about integrating it with Unity is I'm able to get the actual tool running. So this is if you connect a real drone like this guy down here, this is what you would use to configure everything about the drone. So for example, I can go down to the motors, and if I'm trying to say test a motor, I can go and be like, look at this, and then raise the value and then see the different things, see how the motor reacts to that. It also gives us a ton of information and data. So if I want to see the gyroscopes of a real drone or the drone in game as I fly around, by integrating the real flight controller, you kind of see all that data. Another reason too is that the on-screen display, as I talked about, the rendering, everything you see over here is all set up here. As a pilot, you configure what that looks like. You get to choose everything on your screen. And so for example, I can come down here, and if I don't want this angular horizon indicator, I can just turn it off, and then that goes away. So that's a reason to integrate an open source flight controller into your game. Another reason, actually probably the biggest reason, was that I wanted something to compare against. I wanted to know that what I was writing when I actually wrote my own flight controller was realistic. So I decided to integrate Betaflight so I can compare against that. So one of the first concepts we're going to get into Betaflight when we look into it is called rates. And I just mentioned this because pretty much every pilot, every drone pilot knows what their rates are. Rates is a concept that all the pilots have to learn. And it's kind of what we talked about before. If the sticks are at 0, if I'm not touching the controller, then the drone should stop rotating. The rates are the desired angular velocity. It's basically when I change my rotation, it's how fast I want the drone to be rotating on each axis, yaw, pitch, and roll. The flight controller is going to map those stick values to those angular speeds. And it's going to apply some curves to it. And we'll kind of look at this in a second. So this is actually what you'll see if you go into Betaflight and look at the curves on there. Every pilot loves to customize these things. And what this is when I move my stick, it kind of follows this curve. It's not actually just like a straight linear line. And one of the reasons for that is that it gives me precision near this. It gives kind of like a very gentle precision when I'm down here. Also, if you're familiar with dead zones and controllers, usually with dead zones, we just check if it's less than a value, but this actually is kind of a smooth curve way of doing it. But then if I really need to get out of a situation, if I'm in something dangerous, I can go all the way to the side, and then it usually gets exponentially more aggressive. And so this is kind of what it looks like when I move the curves around, as I'm flying. And something to mention too is you'll notice it goes from -1, which is the left side, to 1, which is the right side, and then 0 in the middle. But this value goes all the way down to -670 to 670, and those are configurable. And what that is that's the degrees per second, so how fast we want it to rotate. And so as a pilot, you get to configure that. You get to configure, and as a beginner pilot, you probably want to lower those numbers so that you're not like crashing into things constantly. Okay. All right, so the second concept that we're going to talk about what the flight controller does is called the PID, P-I-D. A flight controller must apply corrections to the motors. This is the thing we talked about, and it's going to read the gyroscope. And it's going to try to do that to achieve your desired rates. Those rates we just talked about, what angular speed you want it to go at, that's going to be part of the PID algorithm. And PID is a mathematical way of reaching the goal. And I just want to mention that even though this is for a flight controller, this is so applicable to any kind of game problem where you're trying to reach a goal with a number. I know it sounds kind of silly, but like the motors are also controlled by the PID. So let's dive into what exactly I mean by PID. Oh my goodness, this is a PID. When I first saw this, it freaked me out. I mean, I'm a math person, but I don't love this. What the heck is this ugly math? This is the proportional integral derivative controller, PID. And we'll break down visually first what that actually means before actually diving into the math, because the math is, it looks way harder than it actually is. It's very easy. Okay. So imagine the green is the goal that we want to reach, and our little guy, we're gonna try to boost him up. And right now, this is like an underwater scene that I put together. And the reason I did underwater is because there's a lot of drag underwater. It's kind of helped me demonstrate this situation. So drag is gonna slow us down, but we're gonna use the distance to the goal because we gotta figure out how much force to apply, right? We can just pick any force. How much force should I apply to try to get to that goal? So we're gonna use the distance. So for example, if I do this, if I run it, it's going to go up, and you can see that vector gets smaller and smaller as I approach the actual goal until I finally reach that goal, and then, yep, there we go, got it. But there's actually a value that I can scale here, and so this is it's just a constant that we get to pick. And I mention this because as drone pilots, you actually, almost every drone pilot configures these values for their drones because there's so much that changes about drones. So if I pick a very high value for this, it means that I'm going to go 10 times the amount of force that I would have used, right? So I kind of overshot the problem. You could see there when I actually hit it, I did reach the goal, but I overshot it and then kind of came back and springed around. Now, underwater, the drag is slowing us down, so it kind of like stops us, you know, but that's us picking the value for the amount of force there. Okay, so now let's take it to space, because that's my favorite thing to do is take these problems to space. And again, an object in motion stays in motion. So we don't have drag anymore. And we see when we launch it, we're picking it, we're going towards it, but no matter what we do, because we're not slowing down, we're just gonna keep bouncing back and forth. And it's gonna keep oscillating, we'll never actually reach the goal. And I think one of the first things that most people do when they reach this point is they kind of think, oh, well, maybe I'll just pick a smaller value. I'll just go down to like, oh, a very little force here, right? But no matter how little you pick, it's just gonna slow down the oscillations. Nothing's actually slowing down our guy and trying to reach that goal. So it's kind of just gonna keep doing this forever. Okay. So just starting with the first part of it, this is useful. The P stands for proportional. And so this whole thing is the P down here. The E of T, that's just our error. So what that really means is what's the goal and where are we at right now? And what's the difference between those? It's kind of just the distance between those values. That's what the error is. And then as we saw before, KP is just a tunable constant that we get to pick. So in programmer terms, because I just think that this math looks really ugly and complicated, but in reality, it's just error equals current minus goal. Very simple. And then the whole P thing together is just KP times that error. And then the output that we're going to use in this particular situation is the scale to the force. But realize that PID controllers, again, can be used in any numeric situation. Okay. So we need to slow down before we reach the goal. Can we predict the future? So can we know, are we approaching that goal too fast? And so what we're going to do is we're going to use the rate of change in the distance. As the distance to our goal gets closer and closer, how fast is that changing? How fast are we approaching the goal? It's kind of like if you're coming to a stop sign, you know you need to slow down before doing it, right? So let's go ahead and launch this. And we see that when we do, it kind of puts on a brake. First, the initial first force goes up very fast, and then it brakes, it slows down. And that's the D in our PID. And so in a similar way, we actually have a constant that we can pick here. If we pick a very low number, it's going to be like, well, we might overshoot the goal because we didn't pick enough, but we still slow down. If we pick a very high number, like 10, we'll get there, but we're going to go very, 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 very slow to actually get there. And so in a way, it kind of acts similar to drag underwater. But notice that we're in space. We're just controlling our amount of thrust that we're using to get up there. Okay. So the D stands for derivative, and then KD is a tunable constant that we get to pick. This D over dt, that's calculus, and I don't expect anybody to know calculus, but just the easier way of saying this is it's the rate of change of the error. So in programmer terms, just because it's always easier for me to understand as a programmer what that actually means, the derivative is equal to the error minus the previous error. Just save the error of the last frame, and then the next frame, subtract that away from it. So it's the error minus previous error divided by your frame delta time. So that's, if your game is running at 1/60th of a second, that's just 1/60th. And in Unity, that would be the fixed frame time, fixed delta time. And then finally, the last whole part, this whole D term is just the KD, our constant that we got to pick, times that derivative. Okay, so the P and the D works really great until we add external forces. So in this particular example, I've got a planet down below, so there's the Earth or something like it, and we've got gravity kind of pulling our thing down. We want to reach our goal, but something is pulling us down constantly. So let's go ahead and try. What we're going to see happens is, no matter what we do, we're going to go up towards it, but we'll never quite reach the goal. And again, as a programmer, I'm like, well, why don't we just, pick a bigger value, something higher than 5. So I'll pick 20, and I'll try to go up. We'll kind of get there. We'll get a lot closer, but we never actually fully reach that value. You can see it's kind of a little bit off here, and you can also see this in the graph. It didn't reach the full value there. And changing the KD won't help either because that's just going to slow it down more. So again, it never actually stabilizes on the goal and then never fully goes away. So the way we're going to try to fix this is we need some history. We need to know an accumulation of past errors. It's kind of like a memory that goes, hey, how wrong were we in the past? And then we're going to use that to fix this issue. So this is the third component of the PID, which is kind of the middle one here. It's the I. It stands for integral. And that's a calculus term, but again, I'll simplify it way, way, way down to simple code. So again, Ki is another tunable constant. We get to pick whatever value that is. And this S symbol here, this actually is summation. I mean, it's the integral term in calculus. But really what we're just saying is whenever we start this demo to whatever time right now, the current frame, just keep summing or adding all the errors up times the delta time. So it's summing the past errors up to inform future decisions. So what that looks like in code is really just error sum plus equals the error we have this frame times the frame delta time. Just every frame, just sum it up, add each one. And then finally, the I is equal to the Ki, which is our constant, times that error sum. Very, very simple. It's way less complicated than the actual calculus that goes into it. Okay, so what does that look like? So now with the integral, if I run it, we can actually reach the goal. And it's because it actually has a memory of what was wrong in the past and is trying to correct that memory. And something I want to point out is when we actually reach this goal, if I do this again, the error is trying to go to 0. That's always trying to reach 0 right up here. And the rate of change in the derivative is also going to go to 0 because ideally the change, we slow down to the point where there's no more change in the error. but the sum of errors is actually not going to be 0. And the reason is, if it's actually, you can see it's like almost -5 down here. The reason is because it's counteracting gravity. So the whole thing right now is, in order to be stable, it has to have that vector that's pointing equal and opposite to be able to stand still. So that's our up vector and our gravity vector. They're countering each other. So again, it remembers how far it was off in the past and adjusts. The KI is small because the error sum can get very large. We're summing it up every single frame. That value can just keep growing. So we have to use a very small value. And if we choose a much higher value, if I choose a much higher value, so I'll choose like 5 in this example and run it, you'll see it kind of works like the KP. We can end up overshooting our goal by too much. And then just for anybody who's a physics programmer, because this is kind of a fun one here, if you say you don't have drag in this situation, so I get rid of my KD down here, so I'm reducing the KD to 0, so very little drag, KI is actually going to cause a problem because it's remembering the amount of error, but we're not slowing down. So it's just going to keep remembering more and more error. And so the problem is actually going to get worse and worse. And this is what causes a numerical instability. You can see that graph on the side there is just going to keep growing and growing and growing. And so it just means keep the KI value down. It's not meant to be like a high value. It's just meant to correct for things like wind on your drone, kind of pushing your drone away. Wow, that guy goes going crazy. Okay. All right. So as a drone pilot, it's your job to tune those values for your drone. So this is an example of a tuned system for this. So if I picked all these values very carefully, and the whole goal is to reach the goal very quickly, like you say I did it in 2.2 seconds, without overshooting the goal. So I didn't go over the top of the goal, and I hit it very quickly. That is the goal of PID tuning. Okay, so how does this all apply to our drone? Well, each axis, the pitch, the yaw, and the roll, are going to get their own PID, their own mathematical PID. The goal is our desired angular velocity. How fast do we want the drone to rotate? Again, if I don't touch the sticks on the controller, if they're all 0, that means I don't want the drone to rotate. So my goal is don't rotate, right? The current is the current angular velocity read from the gyroscope. So that's what the current velocity is, the angular velocity of the drone read from the circuits. So again, in our PID controller algorithm, that's really just saying the error is the gyroscope minus the rates. Pretty simple. The motor corrections are going to be applied by the result of the PID algorithm, and that's going to be done on the flight controller. And then, as I mentioned before, every drone pilot should know how to tune their PIDs. Okay, so now we have all this together, and I wanted to show this slide because this is actually my flight controller that I've written. I'm not using Betaflight anymore, not using the open source one. And I'm just showing the PID for the pitch, so just the forward and backward. I've got the graphs here, the P, I, and the D all down. So it's the same kind of graphs you're used to. And what we're going to see is that now when I rotate my drone, it will stop rotating if I let go of the sticks. And it'll always go to the desired rotation that I'm holding down on the stick. Oops, oh, sorry, I didn't mean to hit that one. But yeah, so if I take off here, when I nudge the control a little bit, you can see as I let go of it, it stops. So the drone just stops rotating. And it's as if it's kind of applying like a brake. Like, and that is the PID algorithm that's actually applying that. And so this is what kind of gets us that snappy response that drone pilots are used to. And it's also like when you get in a situation where you're too close to something and you need to get away, that's how you achieve that, is through that PID algorithm. Okay. So wrapping this up, the thrust force per motor gives us our lift, so lifting the drone up with our throttle. It also gives us the pitching forward and backward by doing the 2 motors in the back and the front and rolling to the side and side. The motors will apply a torque, which is how we do our yaw turns, which is the equal and opposite because they rotate the opposite direction. And then use an open source flight controller because it gives you what the realism should actually feel like, and also gives you a goal to make sure that what you're programming is actually like matches the real thing. Motor mixing is basically how we go from the stick values to the motor configuration. So basically what motors spin up and down depending on whether we're doing yaw, pitch, or roll. The rate is the mapping from the stick value to the angular speeds that we actually want. Again, this is if I'm not touching the sticks, I don't want my drone to rotate. It's also the sensitivity in the curves too. And then finally, the PID algorithm is what allows us to precisely control that rotation of the drone and apply the corrections to the motors on the flight controller. All right. So if you guys are interested, please join the Kinmen Kill drone community and learn to fly for Taiwan. You will be able to actually learn in my game, I promise that. And again, I'm going to release this demo. It's a little weird because I know most people like to release the slides in a PowerPoint. It's not a PowerPoint, it's a whole Unity project, so I'll be kind of giving that out as a build. And again, I'll be posting the custom physics code if you guys are interested, the C source code there. As well as the news and any updates on the game, drone tips and tricks. And also, as always, thank you guys for coming. All right.
好的，我们非常感谢 Trevor Sundberg 帮我们讲解这一次的无人机实作的讲座。那我们接下来进入 Q&A 环节。那麦克风现在在我手上，那有需要的人可以到前面来。
Hello, Trevor. Thank you for the exciting talk.
Thank you.
I do have two questions. So in the real world, obviously everything is powered by physics. However, in the game space, you could have done it without physics by simulating it, like modifying the transform directly.
True.
Which is probably some of the games do it that way, like animated and not physically simulated.
Exactly.
So why do you want to make it simulated? Is it because like you want to get it as accurate as possible so that you can train people?
Yes. So I think a big reason, like, so his question was, can't we just rotate the drone like using just a transform and then just get a very accurate physics response like that, or what looks like a real physics? One answer to that is that if you just rotate the transform directly, you're kind of ignoring the physics engine. So like you will, it's called tunneling through collision. Like if you're on the ground and you just rotate, you'll just suddenly rotate through the ground. You could use a constraint in physics maybe to achieve that same kind of thing. Another reason is also just because when I wanted to learn to fly drones, I really wanted to learn the open source, like the beta flight controller, because there's just so much to that, to actually, getting that, like, just, you saw how many different things in the configuration there was there. There's even a whole language. They've got like a little programming language in there for the drone. And I wasn't able to integrate that unless I actually made the proper physics response, because Betaflight will actually just like, it's expecting those kind of responses from the physics, and it's actually looking for it because it actually has some minor safety features, and unfortunately not doing it physically correct will trip those safety features. Another example of that is like even just running Unity physics at even like 150 frames per second, unfortunately will trip the physics or the safety features on Betaflight because it's trying to read the gyroscope and it's not able to read it at 8,000 frames a second. It's not updating. So it's kind of like, oh, okay, that nothing's happening. So it really was just for me also to be able to teach pilots like the full spectrum of being able to learn how to fly a drone, not just like a racing game where you could just like, move the transform and it pretty much works. But that's a great question. Yeah.
Got it. So the second question is, from the game you're building and like from how good your Mandarin is, I would like to guess that this is not your first time to Taiwan. Can you share a little bit about the story behind it and the connection you have with us?
Yeah, that's interesting. It's actually my second time in Taiwan. I think my whole life I've been reading world news, and so it's like Taiwan has not been something that's been new to me. I've been the constant problem of authoritarian governments has always been something that's always been on my mind, and seeing it happen in Ukraine was really an eye opener. My wife is also Taiwanese too, so that was a big influence too, because I even before I met my wife, it was like something that just kind of irritated me when I constantly see what China is doing to Taiwan, and so. Seeing it happen in Ukraine, like really opened my eyes, and then actually having family here, it was like a huge deal for me. I was like, I can't let this happen. So, not that I can do very much, but I can try to help. So, yeah.
Thank you very much. I appreciate that.
Thank you.
还有一位。
喂，不好意思，我可以用中文吗？就是我想问一个问题，就是我前阵子有看到乌克兰有使用无人机， 就是自主会去攻击目标。那你有可能会想在模拟器导入AI 的一些演算法，让它自主学习变成一种自主的攻击文集嘛，这样子嘛。
So the question was basically, I think if I understood this right, like Ukraine, for a lot of their attack drones now, they're using AI, like they're augmenting their drones with AI. So that includes like vision, being able to control the actual control to hit a target specifically. And that is absolutely something I want to be able to integrate into there. So part of my goal with this game is to actually create a framework that people can put different flight controllers, not just beta flight, but even custom written ones that have AI, vision, because Unity actually has a great way of grabbing the frame buffer and then using vision, like even for the AI training, the RL network that they have, or the RL training framework that they have. And so I definitely want to be able to put that in there. Did that answer your question?
Yes, thank you.
Yeah, thank you.
So small technical problem. So say if I want to learn this stuff today, and like I don't use Unity, but every game engine or framework I use, somebody handle the input for me. So gamepad, Xbox, X input, or keyboard and mouse. So if I were to put this thing into my computer via USB today, how do I reads the input of the value?
Yeah, so the nice thing is it used to not be the case like several years ago, but nowadays this actually just shows up as a joystick. So even in Unity, even if you're using the first version of Unity input, it will show up like as the axes. You can kind of grab the different axes and then configure it. The one thing I will say is that a lot of the input frameworks, like for example, if you use Rewired with Unity, they have a ton of different types of controllers, but they don't really have these controllers in there. So you do kind of have to create a custom mapping because unfortunately, can you grab me the other controller there? These are two different controllers that are different flight controllers from different brands. The axes, even though they're the same, like this is the same throttle and everything else, they actually come in on different numbers or different axes for each one of them. So you do need a screen to help configure the controller before people start using it. So kind of like a calibration.
But actually reading is handled by the general input system already.
Mm-hmm.
Okay.
Oh yeah. It definitely, like I'm just using Unity's general input system right now to read these values. So.
Oh, that's great. Thanks.
Yeah, absolutely. Cool.
Hello, Trevor, and thank you. And I think this is really amazing simulation. And my question is, do you think about how to design a level, like a level design, or how to make a gameplay? And do you think about it, or you just want to make it a perfect simulation? Yeah.
Yeah. You mean the gameplay portion of it? So one of the games I really loved is PUBG. I don't know if you guys play PUBG, but it's a battle royale style game. So as far as the gameplay, it's actually a great question because if you look at all the drone simulators out there right now, every one of them mostly is just a racing game, right? And so it's like, it doesn't give you a lot to like learn other than if you really love racing. That's not really I learned on it, but I don't love racing. I want to do something else with it. And so part of my goal was to create a game that I would actually play, something like PUBG or something like that I could learn to fly drones at the same time. But also creating something where you can kind of ease people into it. Because one of the things, and by the way, at the end of this, if you guys want to try this controller out or whatever, try something out, I will set up afterwards, so you guys can come, find me and try it out. I also have a mailing list and a sign-up thing if you guys if you're interested. But learning to try to teach people to actually fly, it's such a big learning curve. Like it's so hard to actually fly. So a big thing that I'm going to be focusing on is kind of like this little training thing where you're kind of like, hey, just go forward. Hey, just fly here, and it's not really part of the gameplay per se, but it is part of the learning experience to doing it. And then the actual gameplay being a lot more like, go around, loot things, have fun, run around, hide in buildings that are destructible. That's kind of the stuff you guys saw in the first trailer. So, Yeah. I thought a lot about the gameplay. It's very fun.
I think if they have some speed run game, it would be very funny and very interesting.
Okay, can you say that louder? Sorry.
Oh, I mean, if it's like a speeding game, like a speed run game.
Oh, a speed run game. Oh, yeah.
interesting.
Yeah, that would be very cool. Yeah. Absolutely. Thank you.
Thank you.
你要问吗 ？OK， 那我们继续做。
Okay, so your game is more like a military simulator, or and in real life, the drone flying has a lot of like radio interference, or like maybe using the cable drone. So do you plan on adding any of that, or like thermal optic, something like that in the game?
Yeah, so again, my game, the one purpose of it really is to just learn to fly. So I do think there are, like, when I got into it, there are many different types of drones. The fiber optic cable is this, it's a drone that just has literally it's controlled not through a radio anymore. It's controlled just through a cable, like a light cable that goes all the way to it for miles. I do want to add things like that, but my main focus is just on quadcopter drones. Although you mentioned interference, that's definitely part of the game, because one thing that people don't actually know is how, we see a lot of the videos of how successful drones actually are, but what you don't see is how unsuccessful they actually are. I think it's 1 in 8 drones actually hits its target in real life, and that's because there's drone jamming. And a funny reason is a lot of times it's not even the enemy jamming the drone. It's actually your own team jamming drones, because
Too many people are using the same frequency.
Yeah, they're using the same frequency. They're overriding each other. They have to call things in and say, hey, we're about to use this frequency. Please let us use it. So there are a lot of problems that go into that. Although I think for the gameplay side, kind of to answer the question before too, I am going to focus more on the fun aspects of the gameplay, but the realism of the flight. So, there will be drone jamming, but I'm not going to make it where you'd only get to hit 1 in 8 times, because that's just not going to be fun. So,
is it a single player game or multiplayer?
It's primarily multiplayer. I don't plan on doing other than a training mode kind of thing, I don't really plan on having just a single player. I would love to do a whole single player campaign and story and everything, but I think that's just something I need to, not feature creep right now and just focus entirely on the multiplayer. So,
okay, thanks for answering.
Yeah, thank you.
我们今天非常感谢 Trevor Sundberg 帮我们的演讲还有解说。那如果还有其他问题的话，请再找我们的讲师。那今天的这一场讲座就结束喽。
Thank you all.